Hi, so welcome back. In this lecture, we will learn about certain properties of groups. Okay, groups, group elements of groups, and its structures. So properties of various kinds that we will take up in this lecture and probably in the next one or two more. So let's start with elements first. We will try and look at how elements in a group behave. Okay, so when I say group, as I can remind you that a group would mean a set along with the binary operation. Okay, it's a two-tuple or a pair, and to demonstrate the properties of an element, we want to fix an element here. Let A be an element of the set G, which is a group, and for now we want to pick. We will use some numbers which are non-negative numbers. They can be positive numbers or zero. So in other words, non-negative integers. Okay, and let's call them m and n. Whenever you see m, n coming up in the rest of the points here, please understand that they are non-negative integers. Okay, so the first thing that happens is we want to define something. We want to define what is an element raised to an index n. Okay, the power of a to the this is a to the power n. Okay, and the way we want to do this is the way we have always defined powers of raising an element to some power, and that would be if you multiply. When I say multiply, I mean the binary operation. Okay, but as I said, I may use multiply and product and times. All of these words I can use them interchangeably between a general binary binary operation and the special binary operation, which is the multiplication operation, which we have used all our life. Okay, so right. So the way we want to define a to the power n is multiplying by this binary operation. Okay, by the use of this binary operation, a n times. In other words, a dot a this dot and goes on n times. Okay, so I'm not putting braces or brackets here because we were working in a group, and in a group everything is associative. So the operations are associative. In other words, it doesn't matter if you put a bracket here because you can first product these two and then the next one, or you can product this one and then product with this one. So it doesn't matter in which way you product these NAs, they always come out to be the same because we live in a world where associativity is true. Okay, because we are in a group. So a to the power n, or raised to the index n, would be defined a times a, all this goes up to n times. Okay, and we also want to define a raised to 0 as the identity element of the group. Okay, the group obviously has the identity element, which again I'm going to call it 1. I'm going to write it as 1. It's not the same 1 as the number 1 that we know, but I'm using the same symbol. Okay, because that's the tradition. Okay, so I'm defining. So when you see this colon with an equal to sign, it means I'm defining this symbol here, this thing, this quantity. A to the power 0 would be defined as the identity element. Okay, and this is not special to the element a. I mean, a is just some element. You can pick any element, and to the power 0 I'm going to define that as the element 1. Okay, or the identity. Now we can derive a couple of things from just this definition. That is, if you product a to the power m and a to the power n, obviously all these in the sense that we have defined in the first point, if you product these two, you get what we already know. You can add the indices when you multiply a raised to one index and a raised to the other index, okay? This we can prove very easily from the first one, and let's just try that and see how it comes. So when you want to, what is am? A to the m is, of course, you product a m times, okay? Then there are m of them here, and then you product the whole thing. So because you want to multiply with an, you're basically, this is your am, and the whole thing is multiplied with a to the power n. So you have a n times here, okay? Now, of course, because again, associativity is true, there is no need for brackets. I can just simply get rid of the brackets because the group doesn't care which way you take the product, or which terms you take first. And once you get rid of the brackets, you see there are m plus n a's here. M from here, n from here. So again, by our definition, this will have to be a m plus n. Okay, so that's very simple. All right, just from the way we have defined this. Okay, and if one of them is 0, for example, if n is 0, if am and a0, this of course is, so let's do it here itself. If n is 0, then it would mean 1, which is the identity. And if you product, this is a product, so it's an element of G, because closure is true, closure property is true. G is closed under this operation. So this is an element product with the identity. The element remains what it is. So the identity has no effect on it, and that's just am, but that's also am plus 0, because we know nothing happens if we add 0 to anything, okay? Because again, 0 is the identity for addition, okay? We are in a different level here, okay? All right, so that holds for if n is 0 as well. If one of them is 0, that the property is true, okay? All right, what about this one? A to the m and the whole thing to the n, that would be a to the mn. Well, again, it's very simple and straightforward from just the definition. Let's try that. So I have am to the n. Now am is one element of G, because you have am means a multiplied with a m times. That by the closure property is an element of G. So this is one element which is raised to the index n. So you have am, this goes on n times, right? But each of them have MAs in there. Okay, each of them is like this. So there are MAs in there, there are MAs in there. So if you just write them out, you would get MAs from here, MAs from here, go on up to n MAs. So all of them put together, you would have M multiplied by n A's. Okay, so you would really have M and A's over there. Okay, so from each n of these, you're getting MAs, and that's just AMN again from the definition itself. Okay, so I hope this is clear. Okay, it's very, very easy. Just follow the definition and you will get it. What about this one? Again, I'm going to, so let's rub this out. I have to, all right, before that, come to number 4. Here, the one thing, forget this definition now. I'm defining a new quantity here. But what you can show is that this is also true. And let's just show that, okay? And then I'll come to the definition. This property is also true, again, from the very basic definition of what is a raised to n. So let's rub these out. These are our rough works or small proofs. Right. What would you do with this, okay? You have to show that, let's show this from this one, okay? A to the n is an element of G, and we want to find the inverse of that element. We will show that it is this element, okay? So you have an, and I want to find the inverse of an. In other words, I want to find an element here such that this gives me the identity. That's what I want. Okay? Is that clear? An inverse is the element I want, so I want something here which would give me the identity once it is product with an, and so this would become an inverse by the very definition. Okay? Now what is an really translated? This is n times. Now I'm looking for an element here. What I do is I say that this is going to be A inverse put together n times. Of course this will be an element because A is an element of G, A inverse is an element of G, again because G is a group. So this is a valid element of G. So I put that together n times, and therefore the whole thing will be an element of G, so which is the one I'm looking for. And I'm claiming that this will be what I have to put here to get 1. Let's see. If I have no need for brackets, okay? I mean, I can use brackets as I want, okay? If I want, I can I do it for a smaller number so that it's easier, okay? If I do it for n equals 3, I think the proof is very general. So if you can show it for 3, I think you can show it for n. So I think that would be easier to show rather than writing n of them together. So this really is A, and I'm claiming that the inverse of this is going to be A inverse, A inverse, A inverse. Well, let's just work this out. As I said, I can use my brackets freely. So let's just use them for A and the middle one, this one first. In other words, I want to product these two first, and then I'll take care of the rest. This gives me, I'm going to go up because there is more space there. This is going to give me 1 because after all, this is the inverse of this. So A, and I have a 1 in there. But the 1 really has no effect, okay? It multiplies, for example, this one to give you just A, okay? So really what you have is this. And now I'm going to again use the power of associativity to choose any two of these, the ones in the middle, and product them first. That again is going to give me 1. And so I have A inverse. And this one again has no effect. You can multiply this with this one, and this is, it just returns what it is, okay? And then now you're left with this, so this is 1, okay? This is the identity. So really, whatever, 3 was just a number we have chosen. If you had n of them and you put together n of the A inverses, you followed the process, it would come to 1, okay? So what did I do? What is this really? This is A inverse put together 3 times. This one. You see that? So what I've shown, and this is what I was going to put here, okay? And so therefore, the one that I was going to put here, product with this was going to give me 1. That, you know, the notation for that would have been A3 inverse, because I was trying to find the inverse of this element. So really this here is going to be the A3 inverse, but we found that element is actually this, so A inverse 3, so the two must be the same. So here we have it. Think of 3 as n here, so an raised to minus 1 is the same as A raised to minus 1, or A inverse to the n. Okay, so the two are equal, and this is a rule that we already know from what we have learned from our childhood, but now it's true in this general setting. As I said, groups really, what it does is it captures in a general sense the kind of operations we have been using all our life, and so this thing is true. Okay, so therefore let me just get rid of all this rough work here and keep a clean board, just because there are too many things written over here. So this is true, and I'm going to give them, instead of using brackets like these, I'm going to give them a clean name, which is this. So I'm going to call them A to the power minus n, or A raised to minus n. And when you see this, either it is this or it is this. You can use whichever formula you want in whichever setting you like, whichever is more convenient. Okay, they have two meanings in them, really hidden in them. This is the A inverse, or the inverse of this element put together n times, and this is the inverse of A put together n times. Okay, and they're both equal, they turn out to be equal, and so I can call them A raised to minus n. So this is the first time that I have defined a negative index for the element. Here, this was where I had defined a positive index, because A was not a positive, a non-negative index. N could be 0, as it is here. So we started with defining what the index of what would be A raised to a non-negative index, but this is where we have just defined what A raised to a negative index would be. Okay. I mean, if n was 0, it would come out to be this again. Okay, and you can try that. It would be the 0th power of this element, which by definition is 1. Okay. Anyway, so this is the definition of a negative index of an element. Now, once this is defined, you can do more. You can see that the other few rules that we have used all this while are also true. For example, you can now, here you could sum the positive or the non-negative indices. Okay, you can now sum the negative indices as well. Okay, and that's true again because why is it true? Because let's try this one again. It's very easy. A to the minus m would mean this, really. It's A to the minus 1, or A inverse put together m times. So really you have A inverse, A inverse, A inverse, like that. And then you do the same thing. You put A to the minus n. You get, that's just A inverse put together n times. This is n times. This is m times. And now you can get rid of the brackets. And so you have A inverse put together m plus n times. And the way we have defined is that if you have A inverse put together so many times, you just write A minus of that number. So A minus of this number, which is m plus n. And so you can add negative numbers, negative indices as well. Okay, there's no problem with that. We can also define something new here. I mean, you can define what would be A to the m minus n. In other words, Now this gets a valid definition, a to the minus n, and you have am, because am, we already know what it is, and now we know a to the minus n, and so we can define, just as we defined before, we can define the addition of the indices in this manner. So really it's going to be am minus n, and this is you can either define it or you can actually see it. Okay, you can really see it. For example, if my m is 4 and my n is 2, okay, then I have this one, and you can see, so this means that a put together 4 times, and this means that this is what? This is a inverse put together 2 times, right, from here. And so you have a inverse put together 2 times. Again, you can use the associativity to get rid of this one to make it 1. That collapses. Then you get rid of these 2. That collapses to 1. And so finally, so these are gone, these are gone. And so finally, you are left with a square. Okay, and that's just a 4 minus 2. Okay, so you can see that am and a minus n, okay, if one of them is positive or non-negative, the other one is negative, even then this addition rule is, it just holds. Okay, so we have, so far from 1 to 4, what we have really shown is that the rules for the indices that we have used all our life are actually true in this most general setting of a group as well. Okay, we can use them freely, so we should not have any hassles using the rules that we already know. Okay, and by proofs and small arguments, you can show that they are actually true in this setting. So for example, if you get an equation like this, say a and b are 2 elements of G, and if you get an equation like this, what would this mean? This would really mean AB is equal to 1, or the identity. This would really mean that. I mean, I've just used very, naively, I've just used all the rules that I know of indices, and I've just found it, because I know without any tension or without any worries, I know that all the rules that I know are true from these proofs. I mean, you can try to, if you want, you can, for example, you can multiply both sides by a negative 2, which I can, because I have defined it, a negative 2, right? And what have I defined? You can put together a positive and a negative. Again, associativity holds. I can choose these two. By this, I know that this is going to be just 1, because I'm going to take away from the positive number the negative number, and that gives me b squared. And this, if you take away the positive and the negative number, you get 0, and a to the power 0 is 1. So 1 has no effect on b, so you get b. Again, you can do the same thing. You can multiply both sides by b inverse. And, one positive, the other is negative. You can just get a b from here, because you would take away 1 from the 2. And from here, 1 and the minus 1 will give you b to the power 0, which is 1. And so really, that's what you have, okay? So if you, these are things that we already know, and we should not have any problems using them in this new setting now, okay? All right. Now, we define something more. We define what is called an order of an element, okay? If you remember, one of the examples we did when we were doing groups, or we were doing examples of groups, was this group g, which was basically the roots of this equation, x cubed minus 1 to the power is equal to 0. Okay. The three roots that we found were, one, we called one of them omega, and the other one we called it rho, but really it turned out to be omega square. Okay. And you can go back to the lecture where we had covered this. These were the three elements of the set, and only and we used the complex multiplication. This was the complex multiplication in that case, and we found that if we multiply this one and this one, omega cube, you would get omega and omega square. Again, by all these rules here, you can add the indices, and you would get omega cube. But really, because omega was a root of this equation, omega cube would be 1, because omega cube minus 1 is 0. And so we have an example here where an element raised to some power, raised to an index, is actually the identity element, because 1 is the identity element here. Okay. So from that, we can take some, we can use this idea to define, again, the thing that we're doing constantly, and you have to keep that in mind, is that we're taking examples and generalizing those concepts in this theory. Okay. So since we have a case like this where an element is raised to some non-negative integer, and it returns you the identity element, then we call this, we give it a name, we call this the order of A. In other words, it's the minimum non-negative integer, or a natural number is a non-negative integer. Okay. Actually, let's call it, it should be a positive integer, because if it's, when I say non-negative, it includes 0, and a to the power 0 is always 1, so I don't want zeros here. Okay, so order of an element A would be defined as the minimum natural number, minimum positive integer, such that when you raise A to that index, to that n, you get 1. And the important thing to note here is that it should be the minimum possible positive integer. Okay. For example, and in here, 3 is the order of omega is 3, because 3 is the minimum such integer, positive integer, which gives you this equation. Omega was not 1. Omega to the power 1 was not 1, because omega was different from 1. Omega square was also not 1, because omega square was something else. But omega cube turns out to be. So this really is the minimum positive integer, which gives you 1, and therefore the order of omega is 3. Okay. Similarly, we are going to define this in that spirit. Okay. The minimum integer, positive integer, which gives you this equation. If you can't find an integer like this, in that case, otherwise, we just define the order of that element to be infinity. Okay, we just define it to be infinity. That's just a convention. Okay, so we're going to do one little proof here. Depending on, once we've learned this new definition of an order, we're going to show that the order really is the minimum possible number which can give you this equation. Because what this point is telling us is that if the order of an element A is n, and if you get this equation with another integer, m, some other integer, then n must divide m. In other words, n will have to be less than or equal to m. So really, n will be the minimum integer which gives you this equation. Okay, so let's just try and do that. Let's just show this, and this will be a good exercise in order of a group or order of an element. Okay, so what we're doing is we've taken order of n to be order of a to be n. So we have this equation already, and it's the minimum possible integer n such that you get this. Okay, now I'm going to. It says, so this is absolutely given. Okay, I have another integer m such that am is also 1. I have to show that n divides m. Okay, so for example, the way we do this is we can write m in terms of n by the division algorithm. So this is from Euclid, that you can divide any number m by any other number. Okay, so you can divide it with a quotient multiplying the divisor, and there can be a remainder where the remainder can either be 0 or it will be less than n. Okay, I mean it can go up to n minus 1. It cannot be n. Okay, so this is straight from Euclid's book. Okay, and so we're going to do that. We're going to put, because we are given this equation, instead of m, I'm going to put this thing. Okay, so you have qn plus r equals 1. Now, as I said, I can use all my knowledge about indices. I don't have any problems because I've proved that all the rules that we have learned since our childhood are all true. So let's just do that. This means that a qn multiplied by ar is 1, and this really means that you can put n here and you can put q outside. Remember mn, that same thing. But we know what is a to the power a raised to n, that is 1. So you really have 1 to the q, which is 1 multiplied to itself q times, which really is 1. So 1 multiplying ar is 1, but 1 has no effect on any element. It returns you this element itself. So this is what you have. So in other words, if you start with m and if you define m in terms of n like this, you get that a to the r is 1. But there is a problem. The problem is that, if r is 0, then we know it is 1. Okay, because that's how we have defined it, just in the previous board. So r can be 0 here. It can start from 0, go up to n minus 1. But if r is not 0 but anything else, for example, if r is n minus 1, which is less than n, then that would mean that we have a number, we have a positive integer such that, which is less than n, but a raised to this positive integer is 1. But that's a contradiction, because this was supposed to be the minimum, which would give you this equation, because this was the order of a, right? And so this cannot be true. This cannot be true, because you cannot have an integer, a positive integer lesser than n, and still give you an equation like this. That's not possible once you define the order of a to be n. So, and this n minus 1 is just one thing I've chosen out of the whole range. It can be n minus 2, but all of them are not possible except 0. We know that with 0 that is possible because that's how we had defined in the previous board. So the only possible option for r from this equation is that r will have to be 0. And once r is 0, you can get rid of this thing, okay? Because now r has no contribution in this sum. And therefore, this means that n divides m, okay? Of course, this just means that n is dividing m, because m is a multiple of n, okay? Right. So, for example, you can check that with that omega example, omega to the power 6, okay, if you calculate it, if you put omega 6 times, okay, omega really was minus half plus I root 3 by 2. If you do this, you will get 1 again, okay. But then this is the m, and you know that the order was 3 and 3 divided 6, okay. You can check that out, okay. All right. So this is a very important example, a very important point here, very important property, that once you define n, anything else which gives you this will be a multiple of n, okay. Right. And with this in mind, we will just finish this lecture with one last definition, and this is what we would call a cyclic or a cyclic group, okay. I'm going to again define something new here. It's a definition, and it's going to be the last thing in this lecture. So of course A is an element of G. I'm going to define something like this, where A is surrounded by these two, fancy brackets here, and I'm going to call it. So this means, what it means is that I'm defining a subset of G here, okay. It is a to the power n, where n is some integer, okay. So basically, in this subset of G, so I'm defining A to be a subset of G. It's a subset of G. I'm saying that in this subset you can have all powers of A, okay. So of course A is in there because A is a to the power 1. A square is in here. A to the power 3 is in here. A inverse is in here because minus 1 is also an integer. A to the power minus 2 is also in there. So also the identity A to the powers A to the index 0 is also there, because 0 is this thing. So really what I mean by this is A to the 0 is possibility. It's there. A1 is there. A to the 2 is there. All are there. A inverse is there. A minus 2, A to the minus 2 is there. In other words, inverse of this one is there. So all of them are there, okay. This is, and hopefully by now you know that these are all elements of G because of the closure property, okay. You can put together any number of elements and they would still be an element of G. So therefore this is a subset of G. Now what I'm going to show is that if the order of A, if you have this element whose order is a finite number, in other words, it's not an infinity, okay, then we want to show that this, which is defined as a subset, becomes a subgroup of G, okay. So this, with the same same binary operation as G, just restricted to this subset, this will become a subgroup of G. Let's just do this, and this subgroup will be called the cyclic subgroup of G, generated by the element A. I'll come to the definition of it. So I would just want to show this. It's a very easy proof, but it's a very important one. So, as I said, I claim that in this subset, the only possible elements are these, okay? A to the 0, which is of course 1, A square, up to A n minus 1. These are the only possible elements, distinct elements, that is, not two of them are equal, These are the only possible elements of this A, this thing, this subset. How would we do that? Well, first of all, I have to know whether or not this is a finite set. I mean, the way I've written it here is that this could be infinite. For example, this sequence here can go on and on, but I'm claiming that it cannot go on. It will have to stop. Okay. So let's see what would happen if I included an here in this sequence. Well, an is just 1 because the order of A is n. So really, an is 1. So we get the first element back. Okay, so there's no use putting an here because we already have that element. Can I put an plus 1? Well, an plus 1 will be an and then a. But an is 1 and 1 has no effect on a. So this really is a, but we already have a. Okay, so really after n minus 1, we are repeating the same elements we have already written down. So, and that's why the name cyclic, we're going around in a cycle. Okay, we don't need these elements. These are all the elements, the sequence will stop here. Okay, now I also claim something more, is that they are all distinct. For example, a2 from here, a to the 2 will not be equal to a to the 5. Let's say n here is, let's say n is 10. Okay, so this really goes up to 1, 2, up to a to the 9. Okay, suppose if n is 10. Okay, I'm claiming that this is a2, a2 like a squared like that. Okay, I'm just claiming that a square cannot be equal to a to the 5. I'm saying they're all distinct. Why? If it was equal, then, as I said, by the use of my sense of, how I've used indices and powers, I know that this would be a3. You can subtract off 2 from both sides, and this will be a to the power 3 equals 1, which means that 3 is a number which gives me this equation. But that's not possible because the order of a is 10. So this should be the minimum integer, which should give me 1, but here I have 3 giving me 1, which is not possible. So this thing that I started with, saying that can a square be equal to a5, this is not possible because it gives me something absurd. Okay, so in general what I'm saying is that these are all distinct. Okay, right. So let's just prove that this is a subgroup. That's what I want to prove here. What can I prove the closure property? Suppose I take AI from this set, and I take AJ, and I product them with the binary operation. I get AI and I plus J. Okay. And it must be one of them. I mean, it could be here, or if it goes beyond n, we've shown that it is really one of them. So and that's how we have actually defined this. All powers of all integer powers are all right. Okay. So this is closure property is perfectly all right because this sequence is a finite one. Okay. What about the next one, associativity? Well, associativity is always true because we have restricted this binary operation from G to this new subset, and it was associative here, so it should be associative here. So associativity, as I said before, we really don't have problem with associativity because we're dealing with restrictions. Okay. What about identity? Well, this is there, a to the power 0. By definition, a to the 0 is there, and that is 1, so the identity is in there. What about the inverse? So you have, suppose you have ai, and can I put a minus I, because that is an element here? You know, a to the any integer is possible in this. So and we know how the laws of indices work. This is a to the 0 and this is 1. So really this thing is in there, okay? So the inverse of this, because this is an element of this one, the inverse is there, and so you know this set here follows all the properties or all the axioms of a group, and therefore it's a subgroup of G. Okay, it's a subgroup of G. And this is the extra claim that I've claimed, saying that this subgroup cannot go beyond a to the n minus 1. Okay, it cannot go beyond a to the n minus 1. All right, and this new thing that I have defined, this is with the binary operation. This is called a cyclic subgroup of G generated by the element A in G. Okay, that's the definition. Okay, because it goes around in a cycle, and because this order of A is finite, the group itself is finite. I mean, the subgroup itself is finite. And the order of a subgroup, if I can define it, the order of a subgroup really means, so let's just define it. If H is a subgroup of G, then what I mean by order of a subgroup is really the number of elements in the group, in the subgroup. Okay? So the number of elements, the order of, so by this definition, the order of this new subgroup will be n, which is really the order of A. Okay, so that's kind of a small result or a theorem here. Okay, if you have an element which is finite ordered like this, then the cyclic group generated by A, the cyclic subgroup generated by A, will also have n elements, because the order of this subgroup is n. Okay, and this is how it works. Okay, all right. So I think we will finish this here, and take things forward in the next lecture. Of course, as I said, we will be doing more properties of groups, and these will come in very handy, because these are just the preliminaries, and things will get a little bit more complex from here on in. All right, we'll finish it here. Thank you.